First one is conduction. Next one is convection. And third one is radiation. In this one, radiation is very important and conduction is also very important. In convection, we get generally theory type of a questions bit. Okay. We're not going in much depth beta. So in the, if I'm talking about your conduction part beta, in the conduction, the heat transfer is from one part of the solid material to the another sort of the solid material with the oscillations of your particles. That means like a rod is there. If I keep the rod at one end of your hot end, like say somewhere there is a 100 degrees centigrade of a fire, there I'm keeping a rod of 1 meter. You know that after, as the time passes, after certain interval of a time, heat has been transferred from one point to another point due to the oscillations of the molecules present in the solid material. So due to that solid molecules oscillations, the heat energy has been transferred from one point to the another point, I can say. So I can say this one is due to oscillations of, due to conduction is due to oscillation of your molecules. Due to oscillations of your molecules. So in the solids, oscillations is more. In solids, oscillations is more compared to your liquids. And in liquids, it is more compared to your gases. Clear for everyone? So molecule to molecule oscillation is more in the solid compared to the liquid and the gases particulation. Because in the solids, the molecules are very nearer to each other. Clear for everyone? Whereas in the convection, if I'm talking about, this is due to your, in the convection, it is due to your absorption of energies. They move giving the chance another layer part, isn't it? So generally we see this convection in terms of your fluids. Okay, medium is required. Medium is required. Medium is required. Whereas in radiations, okay, this is in the form of your electromagnetic waves. No medium is required. No medium is required. Like rays from the sun travels the larger layers and come towards the surface of the earth particulation. So they are in the form of electromagnetic radiations part, and they don't require any material medium for the propagation. Okay, so oscillations generally occurs where beta? Oscillations generally occurs. Example for this one is the solid rod. Okay, convection occurs in your liquids. Okay, and this one occurs in the form of what? Radiations. In the form of what? Radiations. That means in the gases, liquid, or say for example in your air particulations. Clear for everyone? Clear? Sure. Next one. First and foremost important formula in the conduction, heat transfer. How do heat transfer take place in the solid from one place to another place? How do you do heat transfer take place from one place to another place? Okay, so rate of heat flow beta, anything divided by time is known as of your rate. So here I am taking here, rate is nothing but heat flowing per your unit time. Heat flowing per your unit time, that is nothing but of your dq divided by your dt is known as of your heat. Anything divided by time is known as of your what beta? Heat. Anything divided by time is known as of your heat. So your heat divided by time is known as of your rate of your heat flow, which is nothing but your what? Heat flow. Okay, that is represented by heat flow. This heat flow is directly proportional to right now. Say for example, if I taking a conductor right now, okay, and initially it is at some temperature. So as you heat at one end, so what is happening? Temperature, the molecules will oscillate and energy has been transferred from one point to another point. So that depends upon the length of the given conductor. That depends upon the area of your cross section, and that also depends upon the material, what type of material you're taking place. So that conductivity will be either increasing fastly or slowly. That depends upon even the material plate of relation, and also depends upon the temperature. If it is your θ1 and θ2, or sometimes in some books we write this one as of your T1, or sometimes we write it as of your T2. Now tell me, among these two temperatures, which will be always on higher temperature beta? T1, because we are heating from this rod from here right now. So we are heating from this side. So obviously this energy has been transferred. So whenever it has been transferring from one point to another point, there is loss of energy to the surrounding part. So I can say that this rate of heat flow from in a given conductor is directly proportional to your amount of your heat flow. That is nothing but area of a cross section and temperature difference. So I can say this one right now, dq by your dt is directly proportional to area of cross section. Rate of heat flow dq by dt is directly proportional to temperature difference, that is delta theta, and dq by dt is inversely proportional to the length of the given conductor. Combining this all relations, we write dq by dt is proportional to your area into temperature difference delta theta divided by your length L. Removing this proportionality constant, we get dq by your dt is equals to some constant k into your A into temperature difference, that is delta theta divided by your length L. Okay, so this is your formula. dq by your dt is equals to k into your A into delta T, where k is known as of your what? Thermal conductivity. Thermal conductivity. K is known as of your thermal conductivity. K is your thermal conductivity, A is area of cross section, delta theta is your temperature difference and inversely proportional to the length. That means I can ultimately write the formula. dq by dt is nothing but heat beta. So heat is equals to Ka into your delta theta divided by length of the given conductor. H is equals to Ka into your change in temperature difference divided by length of the given conductor. This is the first foremost formula which you need to remember for doing the numericals part. This is also called as of your heat current. Heat current. Like in electricity, we define current I is equals to dq by dt. Q is here what beta? Charge. Charge flowing per your unit time is called as of your what? Current. That means it is current. So here it is called like same way heat current. Here it is your electric current. Here it is your heat current. Clear? Any doubt in this one? Any doubt in this one to anyone? Clear, beta?
No, sir.
Sure. Let us try to go for the next formula of this one. One more definition in this one is temperature gradient. Temperature gradient. Anything divided by length is known as gradient beta. Anything divided by length is known as gradient. Anything divided by length is known as gradient. Okay, like if I'm taking P by L, pressure divided by length, so this will be called as pressure gradient. Voltage divided by length is known as voltage gradient. Okay, and velocity divided by length is known as velocity gradient. Okay, same way, temperature divided by length is known as temperature gradient. Clear? So anything divided by length is known as of your gradient. So temperature divided by length is known as of your temperature gradient. Clear for everyone, beta? Any doubt in this one? Now see, if I take this conductor beta, and when I'm heating it, isn't it? Here it is theta 1 and here it is theta 2. When I'm heating it from this part, this is your red hot right now. So you're heating this one from here right now. So when you're heating here, obviously we know that theta 1 will be greater than theta 2. Isn't it? Theta 1 will be your greater than theta 2. So if I draw a graph initially with this one with respect to temperature beta. Temperature with respect to your length. Now, how do you get the graph beta? Initially, their temperature is nothing but maximum, somewhere here. As it is crossing the length, what happened to the temperature? Temperature slowly decreases and finally becomes for me 0, isn't it? So the angle made by this one, if I'm drawing any angle right now, so this angle is nothing but of your theta. So this will give me what? Slope, isn't it? So slope is nothing but of your tan theta. That is equals to your dt divided by your tx. Clear, beta? Initially, the temperature will be the maximum, isn't it? Then as the length increases, what happened to the temperature? Temperature slowly decreases. Initially, slowly decreases. So initially, if the temperature is here 100 degrees centigrade, then somewhere here it will become for me 90. Then here it will become 80. Then here it will become 70. Then here it will become 60. Then here it will become 50. Go on like that. It will become for me 0. So slowly there is a transfer of the heat from one end to another end. And after a certain interval of a time, it will become steady. If you're giving this heat continuously for a long interval of a time, then each and every part will get a constant current. That current is called as of your steady state of your current. Like say in a bucket, if it is having 10 liters of capacity, initially when you're filling it, it will become for me 1 liter, 2 liter, 3 liter, 4 liter, 10 liter. Up to 10 liters, it will fill. After that also, if I go on giving the liquid in that one, it will not store it. It will overflow it in that one. So if the rod is having capacity to tolerate a temperature of 100 degrees centigrade, once the temperature has been reached here to 0, and if you're still providing the heat, then the next part will also become 100, the next part also will become 100, the next part will also become 100. Then after an interval of a time, each and every part of a rod will get a constant temperature. That state is called as of your steady state. That state is called as of what? Steady state. So these are the second terminology you need to remember. Next one is of your, you know the, what do you call the resistance beta, electrical resistance part of relation? I'll just compare it with current electricity beta. I'm just writing here, you see, current electricity relations, firstly, so that it will be easy for us to understand. You know that when there is a resistor connected in the series combination, like say there is a resistor R, and this is a terminal A, and this is a terminal B, the potential across this one is right now for me, say for example, V, and there is a flow of your current in this one, I. So when I'm writing the value of your current in this one beta, I is equals to, how do you write beta? V by your R. That is potential difference divided by resistance. Potential difference divided by resistance. If two resistors are connected in series combination, this is having the resistance R1 and this is having the resistance R2. R effective is written as of your R1 plus of your R2. R is known as resistance, V is known as of your potential. In the same way, we are having one more term in this one called as of your thermal resistance. This one is known as what? Thermal resistance. Very important terminology. Don't go in much depth beta, because complete thermal properties of matter is having only one mark weightage. Either it may be from solid, liquid, calorimeter, maybe your gases part, or maybe your heat transfer part of relation. Thermal resistance I am representing by letter RTH. Okay, let's see for an example. We know the formula of your H. H is equals to K into your A into your temperature difference delta theta divided by your L, isn't it? So if I take this K constant, A constant down the relation, I can write this H is equals to temperature difference divided by, this one is L divided by K into your A. So I'm just taking this constant terms in the down. This is a constant, K is a constant. This one is also constant. That is represented by delta theta is equals to your R thermal. So H is equals to temperature difference divided by your thermal resistance. So H is equals to your temperature difference divided by your thermal resistance. Okay, so therefore I can write here, what is the thermal resistance formula beta? R thermal resistance is equals to your L divided by K into your E. So this is an important formula you need to remember. Thermal resistance is equals to your L divided by your K into your E. Is that clear? Thermal resistance relation, H is equals to, if I am writing here, H is equals to your delta theta divided by your R thermal resistance. Or else I can even write H is equals to what beta? Thermal current. Here the temperature difference is equals to potential difference, and R resistance is nothing but of your electrical resistance part of relation. Any doubt in this one to anyone? Any doubt beta? Can anyone tell me the unit of this one beta? Can anyone tell me the unit of K? Unit of your K. See, H is equals to, what is the formula? K into A into temperature difference divided by your length L. So get the K bit out. K is equals to your H into your L divided by A into your delta theta. H is nothing but what beta? Heat current, na? Isn't it? H is nothing but energy, isn't it? Energy divided by time. Is that clear?
Yes, sir.
See, H is nothing but what? H is equals to Q by T, na? Q is nothing but what? Energy. Energy divided by time is nothing but what? Power. So unit of the power is nothing but what for me? Watt. So I can write this one as of your watt into length is measured in meter divided by area is measured in meter square and temperature is measured in your Kelvin. This square and this meter will get cancelled. So unit will be equal to your watt meter Kelvin. This is your unit. Any doubt in this one? So I can even write K is equals to your watt meter inverse Kelvin inverse is the basic unit of your thermal conductivity. I hope you're clear with this one. Any doubt in this one to anyone?
No, sir.
Sure, very good. So I'm going for the first part of relation, next one, series and as well as of your parallel combination of your rods part of relation. Next one is series combination. Series combination. And rods are connected in the series combination, something like this. So there is a rod here right now. Like this. And one more rod right now. Don't go in much derivation. There is no use of this one. This is a length L1. This is of length L2. Final result is same like current electricity K1 and K2. Whatever the heat you are giving at one end, the same amount of the heat will flow from this one, the same amount of heat will flow from this one, and finally will go out in the given condition. I hope you remember this relation, everyone. Do I need to go for the derivation? If you need, I can go with the derivation. Otherwise, we can directly write the combinations here right now. Two rods are in the series combination. Resistance of this one is R1, resistance of this one is R2. So in the series combination, R effective will be equal to your how much beta? R1 plus of your R2. Can I write like that one? So R effective is your L1 plus of your L2 divided by your, this one is your K effective. What will remain constant in this one beta? Area of your cross section, that is equals to your L1 divided by your K1 into your EA plus of your L2 divided by your K1, this one is a K2 into your area of cross section A. Anything is getting cancelled in this one beta? This area will get cancelled. So it is your L1 plus of your L2 divided by your K effective is equals to your L1 divided by your K1 plus of your L2 divided by your K2. Okay, so from this one, if I'm simplifying this relation, we'll be getting K effective or K equivalent is equals to your, this total term will go down right now. Yes, if I'm simplifying this relation, what is the relation I'll be getting better for this one? Can anyone tell me? So it is your L1 plus of your L2. Isn't it? It's your L1 plus of your L2 in the series combination. K effective will be equal to how much better? L1 plus of your L2. 1 by K effective. If I'm taking K effective up, this will go down. So this will be your L1 plus of your L2 divided by, this will totally come down. So it is L1 by your K1 plus of your L2 divided by your K2. So this will be your K effective. Any doubt in this one? You can simplify this one taking the LCM. I can do the numerical depending upon the given condition right now for that. Clear for everyone? Series combination R effective is equals to your R1 plus of your R2. The next one. In parallel combination. In your parallel combination. In your parallel combination. Please try to complete the PYQs of this topic but immediately. Parallel combination. When two rods are in the parallel, that means one above the other. Like say there is one rod here right now. And there is your one rod another right now. It is made up of thermal conductivity K1. This is made up of K2. Length of this one is L. This one is also L. Area of this one is A1 and the area of this one is A2. Outcoming is different. So I can write here 1 by R effective will be equal to your 1 by your R1 plus of your 1 by your R2. So what is the R formula beta? R is equals to your L divided by K into your A. So I can write here 1 by K effective is nothing but what will it be? I can write beta L divided by your K effective into your area of cross section is nothing but equal to your A. Is that clear for everyone? A effective will be equal to how much beta? A1 plus of your A2 because areas are different. So it is your A1 plus of your A2 is equals to, this one is your 1 divided by L divided by, this one is your K1 into your A1 plus this one is your 1 divided by L divided by K1 into your A2. So if this goes up right now, I can write here K effective into your, this one is your A1 plus of your A2 divided by your L is equals to your K1 into your A1 divided by your L plus of your K2 into your A2. This one is K2, sorry. K2 into your A2 divided by L. L and L will get cancelled. So simplifying this one, I'll be writing here K effective will be equal to your, this one is your K1 A1 plus of your K2 A2 divided by your Ka1 plus of your A2, A1 plus of your A2. So this is your K effective formula. So K effective is equals to your K1 A1 plus of your K2 A2 divided by your A1 plus of your A2 part of relation. Is that clear for everyone? Is that clear?
Yes, sir.
Any doubt in this one to anyone? Series and as well as of your parallel combination. Okay. Sure. Next one. Junction law. Next one is about your junction law. Common temperature. Okay. Just I'll try to help you out with the basic things in this one. See here right now, I'm having one rod here right now. Okay. And I'm having one more rod here right now. Something like a fan connection. And here I'm having one more rod like. Okay. So I've got three different rods right now. Heat flowing in this one is, say, for example, H1. This one is your H2 and this one is your H3. And the common temperature is nothing but somewhere here. So this is the point where they are meeting completely. This is having a common temperature, say for example, some theta. Resistance of this one is say R1, resistance of this one is R2, and resistance of this one is say for example R3. Like say if I'm taking the heat flow right now from here, if there is a flow of your heat right now in this direction, the moment it reaches the junction, that heat will go into this rod. So it is your H2 and that will be equal to your H3 here right now. So it is getting divided into two parts. So I can write here H1 will be equal to H2 plus of your H3. Can I write like that, beta? Can I write like that? Can I write the H in terms of your temperature, beta? Like say here the temperature is T1, here the temperature is T2, and here the temperature is T3. Clear for everyone? And common temperature, I'm taking it as of your capital T. If I'm talking about the rod H1, temperature difference will be equal to how much, beta? T1 minus of your T divided by your R1. I know the formula, H is equals to, I can write as of your what? Delta theta divided by your R. Or else I can write this one as temperature difference delta T divided by R. That only I'm writing here. That is equals to H2. In the H2, if I'm going right now, so for this one, this is the temperature T. So here T minus of your T2 divided by your R1, sorry, R2. Sorry, R2. So this will be your R2 plus. In the part of your H3 beta, in the H3 also there is a flow of the heat from the H to your T3. So I can write here T minus of your T3 divided by your R3. Can I write like that? Can I write like that? So I can get the common temperature right now from this one. So this is the way, how do we write the relations? If I'm taking the T common at everywhere right now, I can write this one as a T minus of your T1 divided by your R1 plus this will be equal to T minus of T2 divided by your R2 plus of your T minus of your T3 divided by your R3 must be equal to 0. I can take like this. So from this one, I can get the common temperature. Isn't it? All the incoming currents must be equal to outgoing currents. That's it. What do you call the Kirchhoff first law application? Something I'm doing like that. Clear for everyone? Isn't it? So I can even write this one as of your H1. It is right now inward, na? So if it is right now for me, if incoming current, if I'm taking as of your positive, outgoing current, I'll be taking it as of your negative. That means if I'm taking right now H1, if I'm taking this one as of your positive, so incoming current must be equal to your outgoing current. That means this should be equal to how much, beta? Minus H2 minus of your H3 must be equal to your 0. Okay. Or else I can take like this H1 plus of your H2 plus of your H3 must be equal to 0. That means H1 must be equal to minus of H2 minus of H3. Depending upon the given data, you can write like that. There is no issue in that. Okay. Let me give you one application so you'll get an idea how we are doing these problems based on this one. Okay. What is the formula, everyone, beta? H1
Yes,
is
sir.
equals to incoming current is equals to your outgoing current. I can write here incoming current, heat current must be equal to your outgoing current, must be equal to your outgoing heat current, outgoing heat current. Here also your heat current you can write roughly, that's not an issue. There are so many problems based on this one, better application of Wheatstone bridge principles are also there in this one. As you are LT students, I hope you have a rough idea so that we can do it out very easily. So 5 resistance are being given. If it is undergoing the relation of P by Q is equals to R by S, then the middle term we can remove so that you can do the numericals related to that one. Is that clear, beta? Sure. Let me give you one small problem. Let's say there is one rod here, there is one more rod here, and there is one more rod here. Okay, these are the three terminals, beta. This one is given in the problem as 80 degrees centigrade. This one is given as of your 40 degrees centigrade, and this one is given as of your 10 degrees centigrade. So here, what is the temperature? T is equals to how much? This is the resistance R. This one is also resistance R. This one is also having the resistance R. Can you do it out, beta? Use the common temperature formula, beta. It is a T minus of your 80 divided by your R plus T minus of your 40 divided by R plus T minus of your 10 divided by your R is equals to 0. Isn't it? So these all terms will become for me 0. So T minus 80 plus T minus 40 plus T minus of your 10 is equals to your 0. Isn't it? So all the t terms on one side and remaining terms on other side. So t. So this will become for me 3t. This will become for me 180 minus 40 minus 10. So that will become how much for me, beta? Minus 130. That is equals to 0. So 3t will be equal to your 130. So t will be equal to 130 divided by 3. So this will be your common temperature. What an idea? Any doubt in this one to anyone?
No, sir.
Chalo, very good. Shall I give you one more example? Will you try it?
Yes, sir.
Chalo, try to do this question, beta. I'm having the rod in the shape of your 4 structures like this. This is your common temperature. This common temperature T is equals to how much? At this temperature 25 degrees centigrade. At this temperature it is your 50 degrees centigrade. And at this point it is given as of your 100 degrees centigrade. And at this point the temperature is given as 75 degrees centigrade. Chalo, come on, try to do it out. Temperature of junction is equals to how much? Temperature of junction is equals to how much? Barika, how are you? Yesterday नहीं आए, कल नहीं आए आप लोग, कैलोरीमेट्री की भी क्लास मिस हो गई आप.
कल आई सर मैं.
कहाँ है? जल्दी चले गए सर कैलाश में ने.
हाँ सर.
क्या चल रहा है कॉलेज में अभी?
सर अभी कॉलेज में देखिए आज तो वैक्सीनेशन था तो मैं नहीं गई थी कॉलेज में. हाँ अभी देखिए वो लोग क्या करे, प्रीवियस वीक का पोर्शन पूरा कंप्लीट हो गया तो अभी ये नए वीक का पोर्शन शुरू करें. मैं देखी नहीं अभी क्या है.
Okay, fine. Now come on, try to do this problem, beta. Common temperature T is equals to how much? Anyone? Same rule. Incoming current must be equal to outgoing current. So this is a resistance R, this is a resistance R, this is a resistance R, this is also resistance R. So it is a T minus 25 divided by R plus a T minus of 50 divided by R plus a T minus 75 divided by R plus a T minus 100 divided by R must be equal to 0. That means a T minus 25 plus T minus 50 plus T minus 75 plus T minus 100 is equals to your 0. Okay, 1, 2, 3, 4. So this will be equal to 40. 40 is equals to how much you are getting, you see, beta? 25 plus 75, 100. 100 plus 200, 200. This is 250. So it will be your 250. So T is equals to 250 divided by 4. That means how much? Six में जाएगा ना? 4 6 are 24. That means this is 62 point something. So this is your temperature. Got an idea how to do the such type of problems? Isn't it? Junction, it can be anything, but it may be a triangular part, anything. You can directly take the application and try to do the problem. Clear, beta?
Yes, sir.
So let me give you one more example. See this one. There is a rod right now like this, and there is one more rod like this. There is one more rod like this, one more rod like this, and one more rod like this. And there is one more point. So this is your A, this is your B, this is your C, and this one is your D, and this one is your E. So this is your X, this is your Y, and middle also there is one resistor right now rod. This is your X, this is your Y, this is your X, and this is your Y. Okay, the question is we have got three rods of materials, 1, 2, 3 of materials of rod which are being connected as shown. All the rods are identical in the length and cross section. If the end A is maintained at a temperature of, this one is maintained at a temperature of 2T naught, and the junction E is at a temperature of T naught. This one is at a temperature of your T naught. Find the effective thermal resistance. R effective is equals to your, how much for this one? Given the length of the each rod is given as of your L, area of cross section is A, thermal conductivity of X is K, and that of your Y is 2K. Okay. So K of your X is equals to K beta. Thermal conductivity of your Y is equals to 2K. Length of each rod is equals to X is equals to length L. And for the Y1 also the length is given as L. And for X the area is cross section A. And for Y also it is the cross section is A. Can anyone try it beta? R effective is equals to your how much? Is it obeying the Wheatstone bridge principle beta? P by Q is equals to R by S. So like this is your P, this one is your Q, this one is your R, and this one is your X. P by Q is equals to your R by X. So rod between C and D will be ineffective. Will be ineffective. Any doubt in this one to anyone? T is equals to 25 to 45 divided by, why 245 beta this one? Okay, fine. Clear? So rod between this one will become ineffective. That means this rod can be redrawn something like this. This is one rod. This is one rod. यहाँ पर तो कुछ नहीं है. We are talking about only about this temperature. Here it is T naught, and here the temperature is 2T naught, and here there is a rod A. This one is your B. This one is C. This one is your D, and this one was an X. This one was rod X. This one is rod X. This one is Y. This one is Y, and this rod is also Y. So tell me what is the resistance of your Y? What is the formula for resistance beta? Resistance of Y will be equal to your L divided by your, for Y thermal conductivity is how much beta? 2K into area of cross section is A. In the same way, Rx will be equal to your L divided by K into your A. That means Rx can be written as of your Ry will be equal to, like say Rx if I'm taking equal to your Ry. So Ry will be equal to how much for me beta? R by 2. Isn't it? Are you getting my point? Any doubt in this one?
No, sir.
So resistance of your Y will be equal to how much? That means if I draw that rod right now, here right now, this one is your rod. So this one is your A, this one is your B, this one is your C, this one is your D, this one is your E. Then now tell me the resistance right now beta. A to B resistance will become how much beta? R by 2. B to C resistance is R, C to E resistance is R, and B to D resistance is how much beta? R by 2. And this resistance will also be equal to your R by 2. Is that clear? Is that clear?
Yes, sir.
Now, which are in series and which are in parallel beta? Now see, when the current is going from this one, I'm drawing here, you see, when the current is going right now, it gets divided here beta. Like say here it is I1 and here it is your I2. So from this point to this point, the same amount of your heat current, and here it is right now I2, and here also your I2. That means these two rods will be in which combination beta?
Series.
Very good. This will be in the series combination, and these two will be also in the series combination. Very good. That means this will become for me how much beta? Effective will become how much? Can anyone tell me what is effective right now for this one?
2R.
Very good. This will become for me 2R. This one will become for me
R.
R. Clear for everyone? Chalo. That
Yes.
means ultimately I am having one rod here right now. So if I'm bringing this one right now out, see this one. This total effect is nothing but of your how much? 2R. And this one is nothing but of your R. So I can totally draw it as of your one complete rod right now. From here to here it is one rod, and from here to here it is your one rod. And here it is just a some point. This is a point A, this is your point of your B. So here the resistance is R by 2, here it is nothing but 2R, and here it is nothing but of your R. So this is your terminal of your what point beta? This terminal point is how much I have taken? That is your E. This one is your E. Clear beta? Now this two will be in which combination? R by 2 and R will be in which combination beta? That will be in parallel combination. Very good. Isn't it? That means I can draw this rod something like this. From here to here, A to B, there will be one rod. Then from B to E, there will be one rod. So that means this will become how much for me beta? 2R into your R divided by 2R plus of your R. That means this one is 2R square divided by 3 into your R. So this R, this square will get cancelled. So this one is 2R divided by 3. So this one is your R by 2. So ultimately I can write that the resistance between the point A and as well as of your E. So resistance across your A to E will be equal to how much beta? So it will be your L divided by effective resistance will be equal to your L divided by your K effective into your A. Can anyone tell me what will be the answer right now? So this one is your 2R into your R divided by 2R plus R. So this one is how much I'm getting? So this one is your 2R divided by 3 plus of your R by 2. How much is this one beta?
7R by 6.
7R by 6. So I can say that effective resistance across your A and your E. So I can write here something right now like this. Yeah. So resistance across your A and B will be equal to how much beta? 7R divided by 6. That's it. In terms of length, if I'm writing beta, resistance across your A and B will be equal to 7. R will be equal to, how do you write? L divided by 6 into your K into your area of cross section A. So this will be your answer. Any doubt in this one to anyone? Any doubt?
No, sir.
Clear for everyone? Sure. Have you got what do you call that one schedule with you, beta? Sure. Next one and very important formula, beta. Growth of ice on pound in cold countries. Derivation is not required again. If you need the derivation, I can send you the link. You can go through it, but I don't expect it is been required for you to remember basically. So just write the relations. That is more than enough. Okay. So whenever there is a water here right now like this, there is a formation of your ice on the surface of your this one. So this is your ice. So obviously this will be at your 0 degree centigrade or some minus temperature. Below temperature of water will be at 0 degree centigrade. And you know that water will be contracting from your 0 to your 4 degree centigrade. It is showing the anomalous expansion of your water behavior, isn't it? So growth of your ice on your lake, you can directly remember the relation for this one beta. I can write the relation for this one. What is growth of your ice on this lake? dy by your dt. dy by your dt is equals to your k into your theta is your surrounding temperature divided by your rho into L into your y. Theta is your surrounding temperature. And rho is your density of your ice. Y is your length of your ice formed. Or we can say thickness of your ice formed. And L is nothing but here right now for me, but anyone can tell me latent heat of your fusion. How much is that beta? Length of latent fusion of your ice will be equal to your 80 calorie per gram degree centigrade part of relation. Clear for everyone? So the basic standard formula to calculate the amount of an ice formation is dy by dt is equals to this much. K is your what beta? Thermal conductivity. Okay, so this one is your thermal conductivity. Clear? Of what? Ice. Thermal conductivity of your ice. Clear for everyone? Is that
Yes.
clear? The derivation is not much required, but you can directly remember this relation. That's more than enough. See, if I need to calculate the value of y, that is how much amount of length of ice has been formed. So you can just need to do the integration. Just remember this integration formula. Integral of your x to the power of your n into your dx will be equal to your x n plus 1 divided by your n plus 1. And integral of your 1 by x into your dx will be equal to your log of your ex. And integral of your dx will always be equal to your x. These are some of the basic things you need to remember. Now, if I take this y here, beta, this will become for me y into your dy is equals to your k into your theta into your, this will become for me your d theta divided by your rho into your l. So now integrating on both the side, I can do this one right now. So integrating on the both the side, that is integral of your y into your dy is equals to k is a constant, theta is a constant, rho into your l, integral of your dt, amount of time taken to form an ice and other input. We can write this one. If it is like say from y1 to your y2, I can integrate integral of y into dy is how much better? Anyone? Y square divided by your 2. Limits are right now for me y1 to your y2, that is equals to k into theta divided by rho into your l into your t. So now if I am substituting the limits, integral of this one, upper limit minus lower limit, it will be equal to your y2 square by your 2 minus of your y1 square divided by 2 is equals to k into theta divided by rho into l into your t. Or else I can write here y2 square minus of y1 square is equals to 2 times of k into theta divided by rho into l into your t. Clear? Is it clear? Even time you can take from T1 to T2, beta. There is no problem in that one. So if he's asking the time taken for the formation of an ice, I can write here right now T. So time taken for the formation of an ice will be T is equals to your rho into your L divided by 2 into K into your theta. So this T is right now here. This will go here right now. So this will be equal to your y2 square minus of your y1 square. That means the thickness is directly proportional to your y2 square minus of y1 square, provided remaining all of them are remaining constant for me. Is that clear for everyone? Any doubt in this one to anyone?
No, sir, clear.
Pakka?
Yes, sir.
Sure. So this were the some of the basic things you need to remember in the conduction on which there are the problems you need to do. So I have sent some of the assignments related to this one beta on the app. You can just go through and practice some problems related to this one. Clear? And for calorimetry also beta, I have sent you some links right now. I already have done some good applications on my channel also. So recently I've done for some else. So some of the standard formulas, conversions and temperature and time graph relations also have done. You please guide to go through that one and also send you the notes related to that one. Clear for everyone?
Yes, sir.
Okay, this one was about your story. This is the basic things you need to remember while you're doing. There is don't go much depth related to this topic, purely formula based, and make sure that you try to do some 50 standard questions from your any reference and 50 questions with your PYQs. All the PYQs of your aims, maybe from your aims part affiliation, or maybe your local entrance examination, or from your NEET examination, that 50. That means you make a combination of your 100 questions on that one and try to do this 100 question twice. Or even it may be your thrice. That's more than enough. Okay, 100 questions on heat transfer is more than enough. See, doing that 100 questions and doing them repeatedly, that's only the matter for you right now. Don't try to follow n number of your books and don't follow anyone. Whatever the book you are having right now, from that one simple book or from your app, you write to do or select your 100 questions. In that one, 50 questions should be from your practice booklet, whatever you are having, whichever you feel some good questions are there. That 50 questions you select from that one and 50 questions of PYQ. You first try to complete these 100 questions by seeing, there is no problem. Give 2 days of time or 3 days of your time. Then you try to do this one only twice and thrice. And even the solids, liquids and calorimetry also. Don't go for much depth of that one. I have done some standard relations on my channel. You can just go through, try to do that numerical. That's more than enough for you. Clear?
Yes.
So in tomorrow's session of a class, we'll try to start with your convection and as well as of your thermal radiation. So tomorrow there will be one class based upon your these conditions. Clear, beta? Any doubt to anyone? I'll give you one homework. You please try to do and come. Let us see how many of you can do me this question. And please try to even ask when you are the working of this one tomorrow if you're not getting it out. Good question, which I feel. See here. The figure shows the phase and interface temperature of a composite slab containing of four layers of two materials having identical thickness. Under steady state, that means temperature is same everywhere. Under steady state condition, the value of T is, I'll give the options: 5 degrees centigrade, 2 degrees centigrade, third one is 4 degrees centigrade, and fourth one is 1 degree centigrade. Okay, so please try to do this one and see how far you are getting the answer related to this one. Clear? Figure is also given. Let me draw the figure for this one. One layer is like this, one layer is like this, another one is somewhere here, this one is like this, and this one is like this. All of them are same straight line beta. And here this one is at your 20 degrees centigrade, this one is at your 10 degrees centigrade, this one is your T degrees centigrade, this one is minus 5 degrees centigrade, this one is minus 10 degrees centigrade. This is made up of thermal conductivity K. This one is your 2K. Again, this one is K, and this one is your 2K. This is a given diagram for you. Okay, first one is having 20, next one is 10. Next common temperature is T, then minus 5, minus 10. This is material of K. In between these two, it is 2K. In between these two, it is K, and this one is here right now 2K. Okay. Okay, beta. Take care. Bye.